Myself Sahil Raj, and I am student of IIT Madras in the branch of Electronic Systems. This is my ID card. Now I am going to demonstrate experiment of electronics lab. So let's begin. Going to construct a Wheatstone bridge using resistors, calculate and measure the node voltage and its output voltage, and so on. Here is a list of material and equipment which we required for this experiment. We required 400 kilo ohm resistors R1, R2, R3 and R4, to 1 kilo ohm resistors, to 10 kilo ohm resistors, capacitor in nanofarad range, multimeter, analog board ADLM 1000. This is my theoretical representation of a part 1 of our experiment. Here we can see this is a Wheatstone bridge in which R1, R2, R3, R4 all resistors are 100 kilo ohm, voltage is 2.5 volt. Here we also see that all resistors are equal, which means ratio of all resistors are equal. So this is our balanced Wheatstone bridge. Now we have to find voltage across a node and also output voltage V0. So we know that this is our balanced Wheatstone bridge. So we know output voltage, which is the voltage across a node AB, is directly 0 volt. Now we will find voltage across a node VAC, CB, DD and DA. Now we will find first voltage of our node VAC. To find the voltage across a node AC, we use Ohm's law, V is equal to IR. So we required current across R1 resistors and value of R1 resistor, which is already given. To find the current across R1 resistor, we will first find the total current of a circuit. So total current of our circuit is 0.025 milliampere, which now go and divide into two branch I1, I2. We required current across R1 resistor, which is I1. So value of I1 is equal to 0.125 milliampere. Now we will put all the values in the formula of Ohm's law, V is equal to IR. So we will get 1.25 volt, which is the voltage across a node AC. Now we will do the same with all nodes. Now next we will do the same thing practically. Here is my circuit which I described theoretically. This is my balanced Wheatstone bridge in which there are 4 resistors R1, R2, R3, R4. All those resistors are of 100 kilo ohm. This is the same resistor which I used for a Wheatstone bridge. Let me check the value of these resistors for you. I will check using multimeter. We can see the value is approx 97-98 kilo ohm, which is fine. This is the balanced Wheatstone bridge. We will check voltage of a node and also the output voltage. We will check using multimeter. Let us check voltage across a node AC. We are providing 2.5 volt through ADLM 1000. To check voltage, we will set multimeter to voltage. Here we can see voltage across a node AC is 1.16 volt. Now we will check voltage across a node DB. Which is also of 1.16 volt. Now we will check voltage across a node CD, which is a node of input voltage. Which is of 2.44 volt, which is also okay. Now we will check output voltage V0, which is voltage across a node AB. This is our balanced Wheatstone bridge. So voltage of a node VAB, which is output voltage, will be 0. Let's check it. Here we can see this is 0 volt. So it means this is our balanced Wheatstone bridge. Now we will repeat the same, but we change the input voltage from 2.5 volt to 2.5 plus sin omega t. We will change this value using Pixel Pulse 2 software. Now this is my circuit in which I provide input voltage of 2.5 plus 1 sin omega t instead of 2.5 volt. We will provide this input voltage through Pixel Pulse. Let's see the wire connection. White one is connected from channel A, black from ground and grey from channel B. Here is my Pixel Pulse 2 software in which this sinusoidal is coming from channel A, which is providing input voltage to our circuit. I set the range of input voltage from 1.5 volt to 3.5 volt. This is the channel B, which is measuring output voltage of our circuit, and the output voltage ranges from 0.75 volt to 1.75 volt. I am getting this output because I am giving the input on a formula of 2.5 plus sin omega t. Now we will build a balanced bridge if the components available are 1 kilo ohm, 100 kilo ohm and two 10 kilo ohm resistors. To make a balanced Wheatstone bridge, our ratio of the resistors should be equal from both sides. So I put a 1 kilo ohm resistor in R1, 10 kilo ohm R2. So the ratio of these two become 1:10. Now I put a 10 kilo ohm resistor into R3, 100 kilo ohm resistor of R4. So the ratio of these two become 1:10. So the ratio of the both side is now 1:10. So it means our Wheatstone bridge is balanced. To check our Wheatstone bridge is balanced, we use multimeter to check output voltage. If our output voltage is 0, it means our Wheatstone bridge is balanced. Now we will check output voltage. Here we can see our output voltage is 0.0 volt. So it means this is our balanced Wheatstone bridge. We are doing part 2 of our experiment. In part 2 we have to create unbalanced Wheatstone bridge. To create unbalanced Wheatstone bridge, we are using the same circuit which we used in part 1, but we add just few more resistors. We add 1 kilo ohm of resistor in between R1 and a positive terminal, and more 1 kilo ohm resistor between R4 and negative terminal. To check this is our unbalanced Wheatstone bridge, we will check output voltage. We know which is a voltage across node A and B. If our output voltage is not 0, so it means this is unbalanced Wheatstone bridge. If output voltage is 0, this means this is our balanced Wheatstone bridge. Here we can see in multimeter our output voltage is 0.02 volt. So it means this is our unbalanced Wheatstone bridge. Now we will check node voltage. Let's check voltage across node C and D. Voltage across node C and D is 2.44 volt. Now we will check voltage across node D and A. It is 1.15 volt. We will check also other nodes by doing the same. Now I am going to do third part of our experiment. In a third part, I have to create low pass filter from unbalanced Wheatstone bridge, which we already created in a part 2. So this is my unbalanced Wheatstone bridge and its diagram. This is my R1 and R2, which is of 100 kilo ohm. 1 kilo ohm resistor placed between R1 and positive. This is my R3 and R4 of 100 kilo ohm, and 1 kilo ohm resistor placed between R4 and negative. Now I have to create a low pass filter from this unbalanced Wheatstone bridge. To create low pass filter, first we have to calculate R equivalent of the unbalanced Wheatstone bridge. So my value of R equivalent is 100.5 kilo ohm. So we take approx 100 kilo ohm to create low pass filter. This is my low pass filter and its diagram. R is of 100 kilo ohm, which is R equivalent. C is of 10 nanofarad, and I am giving input voltage from ADLM 1000. This is my white wire, which is connected to channel A, grey connected to channel B, black connected to ground. Now we have to measure the corner frequency using a frequency generator and an oscilloscope available with the analog board. My frequency ranges from 1 Hz to 1 kHz, and I am providing a signal of 2.5 plus 1 sin omega t from the analog board. Here in LPF, we clearly see that it is equal to Thevenin equivalent, in which V in is equal to Thevenin voltage, R which is in series is equal to Thevenin resistor. This is Pixel Pulse 2 software which I am using to give input voltage from 1.5 volt to 3.5 volt to my LPF low pass filter circuit, and also giving frequency from 10 Hz to 1000 Hz and measuring its output voltage. Currently my frequency is 10 Hz and my output voltage is approx 1.8. Now I'm changing frequency 10 to 20 Hz. It's still approximate. Now changing from 20 to 100 Hz. Now my output frequency is 1.67, which is decreasing, and also my RMS is 0.5, which is also decreasing. Now changing frequency from 100 to 200 Hz, we can see that my output voltage is decreasing and also my RMS is decreasing. Now changing 200 Hz to 400 Hz, we can see it is decreased to 1.27 output voltage, and also my RMS is decreasing. We will do till we reach 1000 Hz, and we plot graph of frequency, output voltage versus frequency. In graph, we clearly see that when I increase frequency, my output voltage is decreasing. This is because this is a graph of low pass filter, in which at cutoff frequency 159, my low pass filter is only passing low frequency and neglecting high frequency.